Measurements and the solar system. For this lesson, we'll mostly be focusing on information given by the solar system data table that is located in the Earth Science Reference Table on page 15. First, we have the order of the planets from the Sun, furthest planet Neptune, and then we have additional information at the bottom of Earth's moon. The order from the Sun starts off with a group of planets that we call the terrestrial planets. These are all planets that have rocky surfaces. These include Mercury, Venus, Earth. After the Earth is Mars, and then the asteroid belt. Please mark down on your reference table that these 4 planets right here are considered to be terrestrial planets because they are rocky, meaning that they have a solid surface. Beyond the asteroid belt, we have the gaseous planets. These are called the Jovian planets. They have a gaseous surface. They are not solid. These include Jupiter, Saturn, Uranus, and Neptune. Beyond Neptune, we have Pluto. Some scientists group Pluto with a group of celestial objects known as dwarf planets. Beyond Neptune, beyond Pluto, is the Kuiper Belt, where our comets come from. In your reference table, for Jupiter, Saturn, Uranus, and Neptune, Jovian planets. The next bit of information we get from the reference table is called the mean distance from the Sun in millions of kilometers. Planets do not orbit around the Sun in perfect circles. They orbit in ellipses, which are ovals. So sometimes planets are closer to the Sun, sometimes they're further away. What the numbers indicate right here is the average distance they are away from the Sun in millions of kilometers. So you can see here that Mercury is 57.9 million kilometers in its average. And as you go further away from the Sun, the distance becomes greater. Here's that extra information about the Earth's moon, that the moon is 149.6 million kilometers away from the Sun, but it orbits the Earth at 0.386 million kilometers from Earth. The mean distance is based on the fact that planets' orbits are not circular. The Sun is not at the center, but the orbit is an oval. The mean distance is the average distance. All right, and here's a much exaggerated orbit of a planet around the Sun. The Sun is not at the center. The Sun actually shares 2 points near the center. These points are called foci. As the planet goes around the Sun, sometimes it's closer, sometimes it's further away. So once again, the mean distance is the average distance between the planet and the Sun. Number 3 on the list is the period of revolution. This is the amount of time it takes for a planet to go around the Sun. Starting with Mercury and going further out, you'll notice the greater the distance, the greater the amount of time. With the heliocentric model, planets further away have a greater distance to travel, so they take more time. Let's add something to our notes here. The further away a planet is from the Sun, the greater amount of time it takes for it to complete one revolution. The further the distance from the Sun, the greater the revolution. And we can see that on this chart, that a planet that's close to the Sun has a short distance, takes a short amount of time to go around. A planet further away from the Sun takes a longer amount of time. Number 4, period of rotation. That's the amount of time to complete one spin. Even the Sun is spinning around. It takes 27 days for the Sun to complete one spin. As we look at these numbers, we'll find out that there's really not the same kind of correlation we had before, where as the distance increased, the revolution increased. Planets like Mercury take 59 days. Here's Venus at 243. Our Earth only takes 23 hours and 56 minutes and 4 seconds to make one complete spin, about 24 hours, about a day. Mars, very similar to Earth in its period of rotation. Once we get into the outer planets, we find that these outer planets are really spinning very quickly. A giant planet like Jupiter only takes 9 hours and 50 minutes and 30 seconds to spin. So once again, we don't see the direct correlation. Now take a look. Interestingly enough, going back to the moon's period of revolution and period of rotation are exactly equal to each other. As far as planets go, one of the quirkiest situations is right here for Venus. Venus's year is 224.7 days. So it takes 224.7 days for Venus to go around the Sun one time. But during the course of going around the Sun one time, it doesn't even spin one time. So a day on Venus is actually longer than a year on Venus. So in our notes on period of rotation, the amount of time to complete one spin, there is no correlation between the distance. For Earth's The Earth's rotation defines its day. So a day on Earth is the amount of time it takes the Earth to complete one spin, which is pretty close to 24 hours. Although eccentricity of orbit is not mentioned in your notes, what I'd just like to point out to you is that some planets have a much more oval shape orbit than others, and this is measured in a term called eccentricity. Now, we will learn how to calculate the eccentricity of a planet. What I would just like to point out to you is that the lower the number that you have for these values here, the more close to a perfect circle the orbit of a planet is. So a planet like Venus has a very circular orbit. So does Neptune. But a planet like Mercury has a more oval or elliptical orbit. Getting back to the notes, equatorial diameter, the distance measured through the planet, is the size of the planet measured across the planet. So equatorial diameter is the distance of the planet from one side to the other through the equator. So equatorial diameter here is measured in kilometers, and you can see how large the sun is in kilometers. 1,392,000 kilometers. Starting with terrestrial planets, you find that these are very, very tiny compared to the outer planets. The Earth and Venus are sometimes called the twin planets because of their proximity in size, but certainly not because of their surface conditions. Then we have the largest planet, Jupiter here, Saturn, Uranus, and then Neptune. The Earth's moon, 3,476, is surprisingly just 1,400 kilometers or so smaller than Mercury. So the equatorial diameter is measured from side to side through the equator. And when we compare the two different groups of planets that we have, terrestrial versus Jovian, the terrestrial planets are smaller, the Jovian are larger. Number 6, mass compared to Earth. If you can imagine that Earth has a mass of 1, or a unit of 1, the Sun would be 333,000 times bigger in mass than the Earth. Now, taking a look at the planets, the terrestrial planets are low-mass planets. The closest planet in mass to the Earth is Venus. The outer planets are much more massive, and the Moon has a mass of 1/100th that of the Earth. Number 7, density. Density is found by taking the mass of the planet divided by its volume. When we compare the terrestrial planets versus Jovian planets, we find that the terrestrial planets have a higher density than the Jovian planets. The Sun has a similar density to the Jovian planets. Saturn's density at 0.07 would mean that if there was a giant galactic lake, Saturn would actually float in the water of that lake. The final section on number 8, orbital eccentricity, will be saved for another time. So you can use this solar system data chart to give you all kinds of information about the Sun, the 4 terrestrial planets, the 4 Jovian planets, and also the Earth's moon, which we will study at a later time. The chart gives you the order of the planets, the distance, the period of revolution, the period of the rotation, the eccentricity of the orbit, how circular it is or how oval it is, depending upon how high the number is, the equatorial diameter, the mass compared to Earth, and the density of the planets, as well as the moon and the sun.